The world-class TSUBAME 4.0 supercomputer at the Institute of Science Tokyo officially began operations on April 1, 2024. The system consists of 240 compute nodes, equipped with a total of 960 GPUs, delivering a peak performance of 66.8 petaflops. Building on the original concept of TSUBAME as a supercomputer for everyone, TSUBAME 4.0 evolves this vision into a supercomputer for everyone and more. It offers compute resources to support a broad spectrum of research activities. TSUBAME 4 utilizes HPE Cray XD665 compute nodes. Each node integrates two 96-core AMD EPYC 9654 CPUs and four NVIDIA H100 SX-M5 GPUs, featuring a special HBM2E variant with 94 GB of memory. This architecture achieves a high level of integration between CPU control and the massive parallel processing power of GPUs, enabling accelerated high-performance computing. It delivers robust computing capabilities suitable for diverse workloads, from scientific simulations to AI training. The system achieves an aggregated performance of 66.8 petaflops in double precision and 952 petaflops in half precision, ranking among the highest in Japan. Each node is equipped with 768 GB of DDR5 4800 memory across 24 channels. High-speed wide bandwidth access is enabled by the dual CPUs supporting 192-core computation. Communication is handled by four InfiniBand NDR 200 gigabits per second ports, delivering an impressive total bandwidth of 800 gigabits per second per node. All nodes are interconnected using a full bisection fat tree topology, which ensures high-speed and highly efficient data exchange across the entire system. This architecture enables the system to handle massive volumes of data with minimal latency and maximum throughput. The storage system is provided by the HPE Cray Cluster Store E1000. It includes 44 petabytes of HDD capacity and 327 terabytes of SSD capacity, offering both high-speed and large-scale storage. TSUBAME 4 is housed in 30 racks, with 23 dedicated to compute nodes and 7 for storage and system management. Hewlett-Packard Enterprise oversaw the system's overall design and construction. TSUBAME 4 is installed in a newly constructed data center on the Yokohama campus of the Institute of Science Tokyo, located in Yokohama, Kanagawa Prefecture. The machine room spans 210 square meters. Cooling systems are located beneath the floor and outside the building. Direct water cooling is used for processors, which generate approximately 80% of the system's heat, while indirect water cooling, where air is cooled by water, is used for other components. This setup enables all compute nodes to be cooled using water at approximately 20 degrees Celsius. Power consumption during standard operation ranges between 650 and 850 kilowatts, supporting high-intensity computation while maintaining an environmentally conscious design that minimizes energy usage. The defining feature of TSUBAME 4 is its commitment to the philosophy of a supercomputer for everyone, a legacy carried forward from the original TSUBAME system. Our goal is to make supercomputing resources accessible to as many people as possible. This philosophy is reflected in the software as well. In addition to traditional SSH command line access, TSUBAME 4 introduces an open on-demand web interface, allowing users to operate the system directly from a browser. This enables intuitive job submission, file transfers, and visualization, making high-performance computing accessible even to those without specialized expertise. Job scheduling is managed by Altair Grid Engine, developed by Altair Engineering. It automatically and fairly allocates jobs based on priority, continuously monitoring and optimizing the usage of GPUs, CPUs, and memory. Resources within each compute node are flexibly allocated based on the application, supporting a wide range of workloads, from simulations to AI and data science. TSUBAME 4 combines cutting-edge hardware performance with a software infrastructure designed for usability and operational efficiency, truly making it a supercomputer for everyone and more. From its inception, TSUBAME has consistently embraced the latest technological challenges, paving the way forward. This journey began in 2006 with TSUBAME 1.0, developed by the Tokyo Institute of Technology, the predecessor of the Institute of Science Tokyo. It achieved a top 500 global ranking of 7th, the highest in Japan at the time. The enduring catchphrase, "Supercomputer for everyone," was born with TSUBAME 1.0, which was accessible even to first-year students. The history of TSUBAME is nothing less than the evolution of supercomputing itself. A pivotal moment came in 2008 with the launch of TSUBAME 1.2, which firmly set the direction for the future of the TSUBAME project. It was the first in the world to adopt GPUs on a large scale, opening the door to their use as accelerators for scientific computing, a major shift from their previous role, which had been primarily in gaming and graphics applications. TSUBAME 1.2 became the first GPU-equipped supercomputer to be ranked on the top 500 list. This spirit of innovation continues with TSUBAME 4.0.
HPE built the TSUBAME 4.0 supercomputer, continuing its legacy from TSUBAME 3. The core of the system, 240 units of HPE Cray XD665. It is equipped with a total of 480 AMD EPYC 9654 CPUs and 960 NVIDIA H100 GPUs. Each server node is tightly interconnected with NVL200 InfiniBand, enabling high-speed communication. For storage, the HPE Cray Cluster Store E1000 features 327 terabytes of SSD and 44.2 petabytes of HDD capacity, facilitating high-speed and efficient processing of massive datasets. TSUBAME 4.0 builds on the HPE Direct Liquid Cooling solution introduced with TSUBAME 3. Heat-generating components such as CPUs and GPGPUs are directly cooled, enabling efficient and stable system operation while ensuring maximum performance. TSUBAME 4.0 stands as one of Japan's leading flagship supercomputers, actively serving academic institutions, research organizations, and companies beyond Institute of Science Tokyo. We are honored to be a key partner in this project and see its capabilities being widely used across sectors that drive innovation and discovery. HPE remains committed to providing advanced solutions and robust support to ensure TSUBAME 4.0 continues to operate reliably as a versatile platform to fuel groundbreaking innovation in research and education, fusing science and AI.
We at NVIDIA are thrilled to celebrate the success of the TSUBAME 4 supercomputer at Science Tokyo. With utilization already passing 90%, it's clear that Science Tokyo's researchers and students are eager to move their work onto this new platform. One of the most exciting achievements is the training of Solo on TSUBAME 4, Japan's powerful sovereign large language model based on Llama 3. This is exactly the kind of work we built the NVIDIA H100 Tensor Core GPU for. TSUBAME4's success is powered by our fantastic partnership with HPE, bringing this discovery engine to life with embedded NVIDIA technologies. TSUBAME4 has 240 nodes. Each node packs 4 H100 GPUs with 94 gigabytes of high bandwidth memory. The nodes use direct-to-chip liquid cooling for the GPUs and CPUs. The nodes are connected with our NVIDIA Quantum 2 InfiniBand networking, which gives every GPU its own dedicated 200 gigabit per second lane for communication and massive scalability. Beyond AI, TSUBAME4 is accelerating a vast spectrum of science, from drug discovery to material science, medical imaging, and environmental sciences. Researchers now have the power to solve humanity's biggest challenges faster than ever before. TSUBAME4 isn't just a machine, it's a launchpad for the next generation of discovery. We are proud Science Tokyo selected NVIDIA for the next groundbreaking platform for science and AI. Congratulations again to the team at Science Tokyo. We are honored to be part of your journey.
Altair is responsible for the workload management solution Altair Grid Engine for the Institute of Science Tokyo's TSUBAME4 supercomputer. So what exactly does a workload management system do? Simply, it provides users secure access to CPUs, GPUs, memory, and storage. It ensures that users get their share of the supercomputer by enforcing limits and scheduling policies on the thousands of jobs running in the system. Altair has a long history with the Institute of Science Tokyo and powered both TSUBAME 1 and 3 supercomputers. We continue this tradition with TSUBAME 4. The new system contains 240 nodes, with each node containing 2 AMD EPYC CPUs and 4 NVIDIA H100 GPUs. This new machine needed to handle a mix of CPU, GPU, and non-GPU jobs, containerized and non-containerized applications, including demanding AI jobs. One special challenge was support for NVIDIA Multi-Instance GPU, or MIG functionality, which lets a single GPU be split into multiple smaller GPUs so that multiple jobs can run on the same physical hardware efficiently. But when an application needs a full GPU, Altair Grid Engine can dynamically reconfigure this GPU from MIG mode to non-MIG mode without the need to restart any cluster services. Behind the scenes, Grid Engine Execution Agent enforces CPU and GPU isolation, and GPU reconfiguration happens quickly at job start and job end with minimal overhead. Over the past 20 years, Altair Grid Engine has evolved alongside the Institute of Science Tokyo's HPC systems, meeting the growing demands of modern applications, including artificial intelligence. Altair Grid Engine ensures that the TSUBAME4 CPUs and powerful GPUs, which are 14 times more powerful than the CPUs, are utilized to their full potential.
We are addressing the challenges associated with motors used in next-generation electric vehicles. As the heat generation density of the stator coils increases, we are conducting numerical analyses on heat dissipation. These analyses include two-phase thermal flow, natural convection, and turbulence analysis, all performed using the lattice Boltzmann method. The LDM is well suited for thermal fluid analysis within complex geometries and is easily parallelizable. Since it is highly compatible with GPUs and the target problems are large-scale, we utilize TSUBAME 4.0, a supercomputer optimized for large-scale GPU parallel computation. So far, by clarifying the flow characteristics of the coolant within simplified coil structures and the turbulent fields generated between the rotor and stator, we have obtained useful guidelines for the optimal design of electric motors.
in our research group, we are developing a large language model called Swallow. The name Swallow comes from the logo of Tokyo Institute of Technology, which is the name of our university before it became Institute of Science Tokyo. The Swallow model is continually pre-trained from open source models that are trained in English, mainly in English. And what we do is we continually pre-train these open source large language models using our own Japanese data, along with other data sets from math and code. And we mix a little bit of English so it doesn't forget the original English skills. Upon training Swallow, because it's a very large language model, it requires a lot of computational resources, especially GPUs, because deep learning requires a lot of GPU resources. And then when we want to train billion parameter models, we require tens, hundreds, and sometimes thousands of GPUs, which is only possible with a supercomputer like TSUBAME. Another thing about TSUBAME is that it has not just a huge number of GPUs, but also the software infrastructure to support it. We've been using TSUBAME for a long time. This is actually why we can train these very large models easily. It's usually not so easy to train at such large scale. Some GPUs break, and you have software version mismatches. And so when we train Swallow, the fact that we have been using TSUBAME for over a decade is really helpful. We can debug buggy GPUs or faulty interconnects quite easily because we have developed the test programs to detect them. And so without these tools and without TSUBAME, it would have been impossible to train Swallow at 10 billion parameter scale. So the reason why we need to train such 10 billion parameter scale models is because such large language models behave according to a scaling law, which says that if you increase your data and your model size, then the performance of your model improves monotonically, and it actually follows a power law. And what this means is to train larger and larger models, you need enormous computational resources, both because the model is large and also because the training data set is large, which means you cannot just train on one GPU. You need to train on many, many GPUs. And so being able to access TSUBAME and to use it for long periods of time is the only way we can train competitive large language models and train them for Japanese. This is actually quite unique in terms of training that happens in academia. So usually in large companies which have a lot of capital, they can afford to buy many GPUs and train very large models. This is very different from an academic environment where we are more constrained on resources. However, the access to TSUBAME gives us a very unique opportunity to train such large language models. I view the advantages of having access to such a supercomputer locally is enormous. This is particularly important when we want to train at scale and to be competitive in the era of large-scale AI.
Our group focuses on robotics. We build and run many kinds of autonomous robots, like dexterous robot arm manipulation, navigation for wheeled and quad-wrapped robots, and coordinated behavior with drones. To make robots truly intelligent, we have to run a huge amount of training in simulation. Robots are sensitive to parameter changes, so we repeat learning many times, even in similar environments. That's where TSUBAME's computing power really helps. Because we can run many jobs in parallel, experiments that used to take about a month on our lab's GPU servers can finish in just a few days on TSUBAME. Thanks to this foundation, systems we trained on TSUBAME have won a global competition in embodied AI, and many of our papers have been accepted at top international conferences. We have mostly used TSUBAME for large-scale training so far. Next, we want to tap TSUBAME's compute in real time while running robots in the real world, so we can give them more advanced intelligence.
TSUBAME 4.0 is designed so that its immense computing capabilities can be easily accessed by everyone. It will empower the expanding frontier of knowledge, providing strong support for future research and discovery.